I went backwards. I lost.
All I heard was game. Yeah, this one was a long one. Oh wait, we actually went the same amount of time for this one. Oh, but dude, did you see that the update almost went live?
What?
That Facebook Messenger and Instagram DMs are actually like gonna be like a thing now.
I don't go on Facebook that much though.
Dude, like I don't even go on Facebook anymore. Only reason I still got my Facebook because it was one day on campus where Verizon was just not working at all, which was really weird, by the way. Couldn't make no phone calls, no text messages. Best I could do is open up my computer and message my parents through Facebook Messenger.
Hey, Wade, how are things going with those papers I sent you?
Good. I thought it was just the one, right?
It was just one. You're right. It's just one. So we should probably talk about those at some point.
Okay. Do you want to take a moment after class and talk about it?
No, but if you come to office hours one of these days, we could just talk it over.
All right. Sounds good.
Okay. So we were talking about heat flow. In one dimension. And we were given this bar. We're treating space and time as if they're continuous now. So this is x equals 0. This end is x equals 0, and this end is x equals 1. So this is like x equals a half, x equals a third. Everything falls somewhere between x equals 0 and x equals 1 in this bar. And we're going to insulate the all around this bar. We'll put like a sleeve all around this bar, so no heat sort of flows in like this or like that. Any heat that goes in or out is going to have to go in the ends, unless we insulate the ends too. And we're given an initial temperature profile. So these are our initial conditions. I'll call that T sub 0 of x. These are initial conditions. Like maybe I'll say, so for example, maybe T0 of x is just 20. That means that no matter what x is, when we start off, we're just at 20. Let's say this is in degrees, say temperature in degrees Celsius. So we just take this bar, we let it come to room temperature about 20 degrees Celsius, and then we start our experiment. So no matter where we are, no matter what x is, at the start, the temperature is going to be 20 degrees Celsius. So these are our initial conditions. We also have endpoint conditions. We could say, okay, we'll insulate the endpoints. Or we could say, well, no, when we start the experiment, we'll plunge both endpoints into water at this temperature. So let's just say we'll plunge both endpoints into ice water at 0 degrees Celsius. That means, so for any time greater than 0, the left endpoint, x equals 0, the temperature at the left endpoint, so x equals 0 at time t, is going to be 0 because I have ice water over here. And the temperature at the right endpoint is going to be 0. So this is my x, this is my x, and here's my t. So for any positive time, since I have ice water over here and ice water over here, I'm just going to keep these ends at 0. The temperature at the left endpoint, the very left endpoint of the rod is going to be 0. The temperature at the very right endpoint of the rod is going to be 0. It's going to be right adjacent to ice water. And my goal is to find the temperature at any position I want at any time. So here are my initial conditions. All this is initial conditions. All of these, they're up to here. Those are all endpoint conditions. And my goal is to find the temperature at any time, at any position. So capital T with no subscript here, this is a function of two variables, position and time. I could say find the temperature at x equals 0.75, 3/4 of the way over at t equals, what do we say? Like t maybe is in seconds, I guess. Ten seconds after we start. So find the temperature at 0.75, 10. This would be the temperature at x equals 0.75 meters, so 3/4 of the way to the right-hand side after 10 seconds. That's what this means. T sub 0, this only has one variable because I'm saying that time is 0. And the only variable it has is x, where along the rod am I. So this we're given, the endpoint conditions were given. Our goal is to find what happens to the rod after we start it up. Now, the temperature at time 0 at any x, so at time 0, the temperature is what we were given originally, T0 x. So the temperature at position x at time 0 is T0 of x. That's as long as x is somewhere between 0 and 1, not at the endpoints. At the endpoints, we know it's 0 because I plunged it in ice water. So let's see if we can figure out what the problem is actually asking, get a kind of a visual on it. Is everybody, let me wait till everybody gets that copy down because I'm going to need more Blackboard space. So we just said the temperature at time 0 is just basically the initial temperature profile, which I say cleverly just erased. If we're going to graph that, so T of x0, which is just T of T0x. We said initially the temperature of the rod, this is in meters, this is in degrees Celsius. We said initially the temperature of the rod is just a constant 20 degrees. Let's let T be small or positive. In other words, a short time later. So a short time after we plunge both ends of the rod into ice water. Let me call this T1. So T1, T equals T1. T1 is a small but positive time. So here's 10, here's 20, here's X. So we'll go from 0 to 1 along the X-axis. This is going to be T of X comma T1. Instead of T of X comma 0, instead of the temperature profile at time 0, which we know is the constant 20 degrees, because that's what we started the rod at, this is a short time later. This is still in degrees Celsius. This is still in meters. So we start off with a rod. It has a uniform temperature of 20. Every point in the rod is 20 degrees Celsius. We just put it into a room at about 20 degrees Celsius. That's about room temperature. And we just left it there a long time. The whole rod's the same temperature. So we get our experimental apparatus all set up, and at time 0, we plunge both endpoints into ice water. Still the edges around the rod are insulated. After a short period of time, what's the temperature profile just qualitatively going to look like? What part of the rod is going to be warmest? What part of the rod is going to be coldest? Just use common sense here.
The edges are going to be the coldest.
The edges will be coldest. The very edge is going to be 0 because it's plunged in ice water. And the middle is going to be the warmest, right? Because it takes a while for that heat to flow out of the rod. So if I just plunged it into ice water and left it there for a half a second, the edges are going to be quite cold, but the middle is still going to be about room temperature. So let me just dot in a line of type 20. X equals 1. So the very edges are going to be 0 because they're touching the ice water. And the middle will hardly have changed at all. So here's 1/2. Halfway along the rod, it will hardly have changed at all. So we're going to have something that looks very much like that. Is everybody okay with that? And if t equals T2 is a slightly larger time than t equals T1, so a slightly larger amount of time elapsed since the start. And the middle, eventually the heat is going to start seeping out. The ends are still going to be colder and the middle will still be warmer, but the heat will be seeping out. So it'll still be the highest right in the middle. It's going to take the heat longest to leave there. So this is still at 1/2. But the middle, I mean, even right here, the middle of the rod isn't quite going to be 20 degrees. It'll be a little bit cooler. It looks like it's just about touching there, but it's not really. And over time, these bumps are going to get lower and lower. And eventually, if we leave the ends of the rod in the ice water, we're going to end up with, I mean, the rod's going to be approaching 0, right? We just keep maintaining the ice in the water, keep the ends at 0. The whole rod is eventually going to be getting closer and closer to 0. Do you have a pretty good image of what's going on here? So let's tie this into what we did last time. We were talking about 3-dimensional graphs of a function of 2 variables. So here we have a function of 2 variables, x and t. So let's sort of take all the pictures that we have, and I've already erased one over there, but you have them all in your notes, and put them on one picture. Each of these pictures is basically a slice of a surface. So that's supposed to be vertical. So I'm going to put my x-axis over here. I'm going to put my t-axis over here. So this is in meters. This is in seconds. And I'm going to put my temperature axis up here, and this is in degrees Celsius. Here's 0 meters, here's 1 meter, here's halfway along the rod. Here's 1/3 of the way along the rod, 2/3 of the way along the rod, and so on. And here is, say, 10 degrees Celsius, 20 degrees Celsius. So at t = 0, t = 0 is the plane of the blackboard. This is coming out of the blackboard at us. So t = 0 is the plane of the blackboard. Our initial temperature profile was a constant 20 degrees. Coming out a short distance along the t-axis, I called it T1. So coming out short distance along here. So come T1 units in front of the blackboard. We saw that the temperature profile looked a little different. It was 1 unit in front of the blackboard, or T1 units in front of the blackboard. It was 0 at the ends because I plunged both ends into ice water, but it was still close to 20 degrees in the middle. So it looks something like this. Flatter before I think I would flatter better. And coming a little bit further in front of the blackboard, T2 was a bigger number than T1. It was still 0 at the end. But this was sort of a lower bump. And it wasn't quite as flat. So originally, we're still up at 20 degrees. I mean, this is, we had a lower bump. And if we come even further in front of the blackboard, we'll have even a lower bump. And so on. So these curves, this curve, this curve, this curve, this curve, these are 4 vertical slices of the surface. I want you to have a decent picture in your head of what that surface is all about. That surface gets sort of lower and lower till it's almost flat after a while as the heat sort of flows out of the rod. Not just 4 anymore, now we have more vertical slices of a surface. Do you get what I'm talking about? Does this make sense? So if I go to a particular X value at a particular time and I go up to the surface, that tells me how warm I am at that X value at that time on the surface. And my initial conditions are at sort of this edge of the surface at t = 0, right in the plane of the blackboard. And my endpoint conditions tell me what's happening with the surface at the edges. So my initial conditions tell me what's happening in the t = 0 plane. My endpoint conditions tell me what's happening at the edges over here. And it's my job to figure out what happens in the middle here. This is very much like what we did when we were doing heat flow in one dimension in the discrete case. We started off with an initial temperature profile. You have this like on your Excel spreadsheet, and then you moved 1 unit of time ahead, 2 units of time ahead, 3 units of time ahead. So we were just treating this as if time were discrete. Now we're treating this as if time is continuous, and we have a nice smooth surface. Is this okay so far? Good. So at the moment, we have no idea how to take our initial conditions and our endpoint conditions and synthesize this surface. That's where the differential equations come in. So the problem is, given the initial conditions and the endpoint conditions, how do we find the rest of the surface? And the answer has to do with partial differential equations. What I'd like to do in this course, since partial differential equations is something that we don't even usually tackle in a first differential equations class, or at least very, very little, I want to get a feel for what the differential equation might look like, and maybe give you some suggestions as to the techniques that we have to find them, to find solutions. So I'm going to erase my amazing picture. So I'm going to start asking questions that look very similar to the questions that I asked when we were doing this in the discrete case, where we considered the rod to be built out of a bunch of cells and time to be discrete, time 1, time 2, times 3, where you built the your Excel spreadsheets. We're going to play, is it getting warmer? Is it getting colder? So consider a section of rod. So now I'm not going to tell you what's happening at the endpoints. I'm not going to tell you anything like that. So consider a section of rod. And let's say we're given a current temperature profile. Whatever time it is, this will be the current temperature profile. And I'm not saying the endpoints are plunged into ice water or anything like that. You don't know anything like that. I'm just going to give you a little section of rod with the current temperature profile. Let's say in our section of rod, this is temperature. Let's say the temperature is constant in that little section of rod. And we're at some position in the middle of that section of rod. Here's X. is the temperature at X getting warmer? Getting colder? Or not changing? The temperature is constant in that section of rod, and I pick a point in the rod in the middle of that place where it's constant temperature. Is it getting warmer, getting colder, or not changing at all?
Not changing?
Right, it's not changing. The heat's, I mean, it's constant temperature here, so heat's sort of flowing in all directions about the same rate, so it's not changing. So, not changing. Does that make sense? Not changing? I mean, if I have a piece of the rod, let's say this whole section's at like 20 degrees Celsius, this is at 20 degrees Celsius, this is at 20 degrees Celsius, heat is flowing all the time, but heat flows from warm to cold. So if all these parts of the rod are the same temperature, then heat's flowing in both directions at the same rate. Heat's flowing into this little point at the same rate it's flowing out of that point. So it's not changing. Here's a slightly harder one. So again, temperature is height. Let's say I have a section of the rod where the temperature is sort of increasing linearly. Here's my X. Same question. Getting warmer, getting colder, or not changing? You can definitely see heat's flowing in this direction, right? Because it's warmer over here, a little cooler, a little cooler, a little cooler. So heat's flowing in this direction.
Would it
But-
be warmer?
What's that?
Warmer?
So you're saying it's getting warmer. What's your reasoning?
If he's flowing in that direction, it should be continuing.
So heat's flowing from this point to this point, heat's flowing from this point to this point. Basically, we're asking ourselves, how fast is heat flowing into this point versus how fast is heat flowing out of this point? If heat flows in faster than it flows out, it warms up. If heat flows out faster than it flows in, it cools down. So what can you tell me?
Getting cooler.
Getting cooler? So you're saying heat flows out of this point faster than heat flows in. Basically, the rate of heat flow has to do with the slope of the line. So if I have something like this versus something like that, in both cases, heat is flowing to the left. But here it's flowing to the left faster because it's getting colder much faster. So this is how you can feel heat in your hand. When I'm feeling how warm or cold something is, it's because heat is flowing into the surface of my skin and my nerves pick it up. So if the thing I'm touching is much hotter than my hand, the heat flows into my hand very rapidly and I feel it very warm. If the thing that I'm touching is a little warmer than my hand, heat is still flowing into my skin, but it's flowing into my skin at a much lower rate. So over here, you can see that the slope is constant. So heat is flowing here, it's flowing here, it's flowing here, all at the same rate. So is this point warming up or is it cooling down or neither? We're sort of running out of answers here.
Be neither because both sides of the slope are the same degrees.
Exactly. Heat's flowing in at the same rate heat's flowing out. So it's neither warming up nor cooling down. You answered this exact question when we were doing this in the discrete case. And I think it's a little bit harder to understand here, but you already have that other experience to fall back on. So again, it's neither warming up nor cooling down. And it would be the same if I did it like this, because heat's sort of flowing at the same rate this time in the other direction. So neither warming up nor cooling down here, neither warming up nor cooling down there. What if I have something like this? Here's my X. So heat's flowing in this direction because the rod's getting cooler in that direction. It's flowing a little bit here, it's flowing a little bit more here, it's flowing a little bit more here, it's flowing faster here, flowing very fast over here because it's steeper over here. Heat's flowing from warm to cold, and the steeper it is, the faster it flows to adjacent points because the greater the temperature difference. So is this point warming up or is it cooling down? Is heat flowing in faster or flowing out faster?
Flowing out faster.
It's flowing out faster, right? So it's cooling down, exactly. So it's cooling down. Because since heat's flowing out faster than it's flowing in. And it'd be the same if I drew it like this. Heat's flowing faster and faster as I move from left to right. Heat's flowing out faster than it's flowing in. So it's cooling off. So it's cooling off at this X, it's cooling off at this X, basically cooling off everywhere on this hill. And so if I have something like this, it's flowing very fast over here because it's pretty steep. No, it's all flowing to the right the whole time, but it flows sort of slower and slower as this gets less and less steep. So here heat's flowing in faster than heat's flowing out. So this is heating up. So let's say this is your temperature profile. Let's say that's your temperature profile at a certain time. That's supposed to be straight. It's supposed to be a straight line right there. Decide which parts of this are heating up and which parts are cooling off, and which parts are not changing at this instant. So go as far as that to stop actually. At this instant, are these points heating up or cooling off, or neither?
Heating?
They're heating. And so the points between here and here, so heat's sort of flowing at a constant rate. So if I pick a point over here, you can see heat's flowing in at the same rate it's flowing out. So what can you tell me about these points over here? Just at this instant. Later, I agree there's going to be some heat flowing in. But at this instant, what can you tell me?
Maybe neither is happening from right there.
Exactly. So from here to here is neither. What about the points? Well, what about the points from A to C? Are they heating up or are they cooling off or neither? It's easy to see right at B. You can see at B, heat's flowing both that way and that way. So heat's flowing out of that point, but it's still true at any point between A and C. Over here, you can see heat's flowing out of there faster than it's flowing in because it gets steeper as I go to the right. So what's happened to all those points?
They're heating up.
If heat's flowing out faster than it's flowing in?
Oh, sorry, they're cooling down.
Yeah, they're cooling off, exactly. And to the right, here's where they're heating up because heat's flowing in faster than it's flowing out. So here they're heating up. Just in this very instant. I agree, if we let this run over time, who knows what's going to happen over time. But in this instant, here they're heating up, here they're cooling off, and here it's neither because it's a straight line. So in terms of language that you learned in calculus, I just mean calculus 1. What about the curve controls whether a section is heating up or cooling off? What feature are we talking about in the curve which controls whether a section of the curve is heating up or cooling off or not? Just using the language of a calculus class.
It's time derivative.
No, I mean, looking at this picture, you can see that this part is neither heating up nor cooling off. This part from here to here is cooling off, and this part is heating up. So just use what can you tell me about the shape of the curve in those 3 sections that's controlling that? Yes, Jalen. Jalen, did you have your hand up?
I was stretching. I'm sorry.
Oh, okay, that's good. No, feel free, stretch. So clearly the curve has a different shape here than it has over here. And these two regions have different shape than they have over here. What's different about these three sections of the curve?
That it's a parabola. I don't know. I don't know where you want us to go with this.
Yeah, well, you're getting close. I mean, we don't know if that's a parabola, but they're definitely different. I mean, this one's sort of curving downwards. This is sort of curving upwards, and this is neither curving up nor curving down. What do we call that?
Is it like a sine curve or?
Yeah, a little bit like a sine curve keeps switching from curving downwards to curving upwards to curving downwards to curving upwards. Do you remember what we called that in Calculus 1? This business of curving up or curving down?
The period?
Well, a period is the time for one complete cycle, like from here to here. But what do you call this business of curving down or curving up?
A wave.
I think I'm not. So a parabola curves up all the time, right? That's not really a wave, but it curves up all the time. Like a W-shaped function curves up for a while, then it curves down, then it curves up. It's not a wave either, but it has these regions where it's curving upwards. In other words, curving downwards, one where it's curving upwards.
The max and the min?
Well, the max and the min are at these peaks and these valleys over here. I'm trying to, maybe you just don't remember the word, which is possible, but we.
Polynomial?
Well,
No.
polynomial describes this curve and this curve, but not this curve.
What letter does it start with?
With a C.
Concave?
Yes, right, exactly. That's it. The concavity. Remember concavity? So this part is concave up, and this part is concave down. This part's concave up. Here we
Nice
have
one, Terrell.
concave down, concave up, and here it's neither concave up nor concave down. So this depends on concavity. Exactly. Is that something you remember? Maybe my question was too vague. But do you remember concavity? A little bit. Okay. Jalen, I want you to review concavity because that's important in a lot of different courses. How did you find concavity when you were back in Calculus 1? What was it that you did to find concavity? So to find like where a curve is going uphill and where it's going downhill, you took the derivative. What did you do to find concavity?
You could take the derivative on either sides of like the turning point, and if it's like where they cross, if it's above the line, then it would be concave up, and vice versa.
Yes, I know exactly what you're saying. What you're talking about is called the first derivative test, and you can use that to classify maxima and classify critical points as maxima and minima. But there's actually something else that tells you concavity. Let me
I thought you'd take the derivative twice.
Ah, yes, that's it. Ah, you remember. Yay. So this depends, so concavity depends on the second derivative. So let me just rewrite what we just said over here. Oh, goodness. No, I will wait until next time to state, I'm going to rewrite this and then, but think about this, because what you're doing is working out your first partial differential equation basically from scratch using things that you know are true about the real world, about how heat flows. And we were just about set up to sort of write the punchline of the whole joke. So think it over, and we'll talk. We'll pick it up here at the beginning of next class. Are there any questions? All right, cool. I'm really pleased with what we did today. I'm really pleased with your understanding so far, because I consider this to be pretty darn advanced stuff. Okay, I will see you all on Friday.